Hello everyone, welcome to 𝗓𝗃𝗧. So this is the first video of 2023 and I'm going to start a whole new series on foundation analysis and design. And in this series I'm going to use a software which is a very popular software, SAFe 2016, for foundation analysis and design. So this is the first lecture of this series. Let's get started. First of all, what I will do, I will take a small problem statement, and taking that problem, we'll be seeing how we can analyze and design the foundation. And also in further videos, we'll be explaining the other concepts too. Okay, so let's get started. So in this session, what I will do, I will take a small problem with only, you can say, axial load, so there will be no moment added. So here suppose we have a column on which the load of the superstructure we are getting PU, and here I will write the dead loads and live loads. So this PU comprises of two loads, suppose dead loads and live loads. Okay, so here this PU is nothing but the load from the superstructure, so including this column, right? So suppose we have a dead load of 1000 kilonewton and live load of 1300 kilonewton here. Fine. And the dimension of this column, if I say, so this is suppose 450 mm by 450 mm. Okay, so this is the condition in the superstructure. What we have given, we have given a fixed support here, right? This is the fixed condition. So here we need to provide the foundation, right? So this sizing of the foundation we don't know. This thickness also is not known to us, so this thickness also known to us, right? Now one more problem statement, that from, suppose this is my ground level, so from ground level the depth of foundation suppose we are considering as 1500 mm or 1.5 meter. Okay, so this area will be excavating and then we will construct this foundation. So all these areas here we will be having soil filling. Okay, so I will write it as so here we will be having filled up soil, right, excluding this particular foundation area. So now a few you can say inputs I'll be giving. So the grade of concrete we'll be using is M25 grade of concrete. Grade of steel, here grade of steel means rebar, okay, not structural steel. So grade of steel, it will be suppose Fe 500 grade. Okay, one more you can say input that we'll be needing is the SBC, safe bearing capacity. So I will write it as SBC, safe bearing capacity. I'll denote it as QA is equal to suppose 300 kilonewton per meter square, right? So what it will do, now we are getting the load from the superstructure, and at this location, the contact point of column and footing, the load will be distributed to the footing, right? And from this footing it will be coming to the soil, right? And from here what will happen? From here, so this is my soil. So obviously, as we are giving some action, so we will have some reaction here. And this reaction will be getting in terms of ground bearing pressure. Ground bearing pressure, or bearing pressure you can say. So what will be our concept? That the safe bearing capacity of the soil here, that we are getting 300 kN/m². Okay, the ground bearing pressure that we are getting, that means that amount of pressure the footing is extracting to the soil, right? So that's why the same amount of reaction we are getting. So this pressure that we are getting from the footing to the soil, this pressure should be less than this 300 kN/m², right? Then only the soil will be able to you can say take that particular pressure, take that particular load, right? So this is the basic concept of foundation design. So this is these things we all know, so I'm not going in deep in this. So here so how to find this initial sizing, or how to do this initial sizing of the footing? So as I said, that this PU, I will not write PU, actually I'll write P, okay, because service load I'll be writing. So this is my service load P, not PU, okay. Ultimate, it's not ultimate load, this is the service load, fine. So my concept will be that the load I am getting, okay, from the top, and it will be distributing by the footing area to the soil, right? It should be less than my QA. It should be less than my QA. So in that case what will happen? Less than or equal to, you can say less than or equal to my QA. So that means if I just make it P by QA should be less than or equal to my area, right? So this is how we can find out the required area. So what is the required area that we'll be needing? Here I'm just designing it or sizing it for the axial load. I have not added any moment in it, right? So in the next case we may take the moment. So now for this area, how we can find this area? So the service load, we know what is the total service load. So the total service load is the total service load is 1000 plus 1300 kilonewton. Okay, so this is the service load, which is 2300 kilonewton. So this is the service load from the superstructure. Now if you see that we'll be having this footing also, this foundation also will be having, right? So this foundation also will have its own you can say self weight, so it will be also coming here, right? So what we will do, as we have not decided the depth yet, because it will be decided in the different criteria. So what we will do, we will increase this load, we will add some 10% load on this. So what we will do, for sizing of footing, initial sizing of footing, we will do like this, that this 2300, so this is my kilonewton, multiplied by 10% increment, so 1.1 divided by my 300 kilonewton per meter square, which is my safe bearing capacity. Now if you see here, it is pretty simple, that from the units itself you can see that this kilonewton will get cancelled, this meter will be going up, so we'll be getting some area here, right? Okay, so what is the area we are getting here? If I just calculate here, so it will be 2300 multiplied by 1.1 divided by 300. So it will be around 8 point. So the required area is around 8.43 meter square. Okay, so we can round up it and we can go to 9 meter square. So this 9 meter square area of footing is required, okay, which will extract some pressure which will be less than or equal to my 300 kilonewton meter square load. Now this is very initial sizing, because now you can see that we also have this you can say overburden load or the filled up soil on top of it. So this load will also be coming to on the foundations. That we will see. We can do it here also manually, very simple process, but what I will do it in safe. Okay, so now, so basically what is the initial sizing we'll be taking? So our column is of 450 by 450 and we'll be taking a footing, we'll be taking a footing of what size to match this you can say 9 meter square. So it is pretty simple. We will take 3 meter by 3 meter. Now why we are taking square? Because if you see, this is a square shaped column and the load is getting distributed like this. Okay, so by seeing this diagram, you may say that it is better to take a circular footing. Yes, it is always better to take a circular footing, but like in terms of the pressure distribution. But if you see, if we provide a circular footing, in that case what will be the issue? Suppose we have given a circular footing like this. So in that case, the reinforcement that we will be laying, or even the formwork that we will be needing, it will be very difficult to construct. So if you provide the reinforcement like this, so at every single span or at every single, you can say a distance, we will have to cut a different size of reinforcements. So it is not feasible in terms of the you can say construction. So that's why we will not provide circular footing. Instead, as our column is square, so we'll be providing a square footing. If it is a rectangular column, what will happen? So suppose this is a rectangular column like this, so we will always try to size the footing like this, because the pressure will be distributed like this, right here also. So the area requirement will be higher in this direction. So if you just make it square like this, here maybe you will see that the area requirement is not meeting. Okay, so that's why we will size the footing in such a way that we will the load will be distributed equally, or you can say properly in the footing also. Fine. So now what will be the initial sizing that we'll be taking? The initial sizing we'll be taking as 3 meter by 3 meter. Fine, this is the initial sizing, and our column, we know it is 450 by 450 mm. Okay, so now I will jump into the software, safe software. So let me just minimize it. So I will go to this safe 2016 software. Here you can see pretty simple interface. Those who have already used 𝗃𝗃𝐃𝐵 or any CSI software, the interface is pretty similar to that. So I will not explain the interface one by one. While doing the project, you will easily understand how the interface works. Okay, or if you want to see some other videos regarding 𝗃𝗃𝐃𝐵s and other CSI softwares, you can look to my other you can say tutorials also. Okay, so to start a you can say new project in safe, I'll go to file, I'll go to new model, and first of all what I will do, I will set the units. So here you can see it is currently in metric units. So if I just modify, obviously we'll be using the metric units. If you want to use the you can say feet inches, so you can go to use US defaults. Okay, so metric defaults, it is already set, so I'll click on OK. I'll change the code and I'll be selecting IS456 because this is the design code that we'll be using. In the design preferences, I'll go to modify show, though these things can be done later also, but I'll do it here itself. So the code is selected, the material safety vectors for rebar and concrete is given, minimum cover for, as it is a footing, so I'll give 50 mm for both top and bottom, and the preferred bar size, so I'll be taking a 16 mm. Okay, so why this preferred bar size? Because when it will decide the reinforcement area, so it will be needing some effective depth, right? So based on this cover and the preferred bar size you have given, it will calculate the effective depth, though it is not required if you do manually, or if you just take the analysis force and do the design in Excel sheets or your own, I can say, MathCAD sheets, so that is not required. But if you are designing it here, these things are I can say pretty required. So though doesn't matter whatever reinforcement I can say you provide, we can always calculate it manually, or we can change it later. So I'll just click on OK, and here I will take a blank page, so I'll click on this blank. So this is the interface, sorry, this is the area where we'll be modeling the foundation. So first of all, I'll take a point which is the column point, so I'll go to draw points, and here at the very origin I'll take the point. You can see the point is created here. I'll close this by selecting this select cursor. Fine. Now I will define some load patterns, so I'll go to define load patterns. You can see the dead load and live load is already defined, and I will define another load case for the overburden load. So suppose I'll just give a load name as Q. Whatever you want, you can provide as per your practice. I'll keep the type as other, and I'll click on OK. I'll go to define and load cases, and I'll check whether the load case is defined properly or not. I'll modify it. I'll also check whether the load pattern is selected here. Okay, so I'll click on this OK and OK. Now I will define the materials. Before that, I will close this, or I can say I will remove this horizon. So I'll just go to this set display options. I'll uncheck this horizon and click on OK. So it is a very blank page, which is good to see. Now I'll go to define material properties. I'll add a new material. So I'll click on this add new material. I'll take a concrete material. I'll name it as M25. I'll change the unit weight of concrete as 25 kg/m³, all we know. Modulus of elasticity 5000 root FCK, so we can do the math itself here. So 5000 root SQRT square root, then you can put the FCK value and press enter. So you got the 5000 root FCK, and then FCK will be changing here to 25 Newton per mm square. Okay, remember, if it is not FCK and you are getting FC dash, so just close it and change the design code from this design section again. So in this design section, you will see this design preferences. Okay, so you can always change it to IS code, and then you will get this FCK. Okay, otherwise you will not get FCK. Fine. So I'll just press OK. I have defined the concrete, and now I will be defining the steel. So I'll just go to add new material again. I'll change it to rebar. I'll make it HYSD 500. Unit weight of steel, so it will be 78.5. Modulus of elasticity 2 into 10 power 5, so 12, 1, 2, 3, 4, 5. This will be 500 grit. Now in while designing, nowhere will be using the ultimate tensile stress. We'll be using the yield stress itself. So a value of maybe 540 or 550, you can keep it here. Otherwise you have to see the code, and you need to I can say put the exact value, but this value is nowhere required actually in our design calculations, right? So you can keep it any value, like maybe 10%, 500 multiplied by 1.1 you can do, and whatever value you are getting, then put it here. It will not change your design result. Okay, so I'll just click on OK, and I'll click on OK. So the material definition is complete. Now what we need to do, we need to define the footing, right? So for that I'll go to define slab properties, and I'll click on add new property. Here first of all I'll select the you can say slab material as M25 grade of concrete, and let us take an initial thickness of suppose let us begin with 400 mm. Okay, so I'll just give F1 400 thick. Okay, I'm starting with 400 mm. I'll change the thickness to 400, and I'll change it to, even if you keep it slab doesn't matter, but I'll change it to footing here. Okay, it will be thick plate always, and I'll click on OK, and I'll click on OK here. So I have defined the slab properties, I have defined the material properties. Now let us draw the footing here. As our footing is a square shaped footing, or whatever shape footing, but it is a concentric footing because the load is there at the center of the footing. So in that case we can use this option, quick draw areas around the point. So I'll just click on this. So the dimension of our footing is 3 meter by 3 meter. It is the property F1 400 thick, and it will be a rectangular slab. Type of object will be slab. I'll click on this origin. So you can see how easily we have drawn the footing. Fine. Now you can, what you can do, you can just to see your column, just for seeing purpose, it will not be I can say used in the analysis or design anywhere. Just for your visualization we can draw a column area also here. So I'll just click on the same option. I'll make it a column of 0.45 by 0.45, 450, and I'll change this property to, let me just turn off this, I'll change this property to none property. So it will be a null object. Okay, so I'll just click on here. So you can see a area will be created which has no property assigned. Okay, it will be only used just for your visualization purpose. Fine. So what we have done, we have created the initial sizing of the footing. Fine. Now what we have to do, we have to assign the loads. So where we will be assigning the loads? So we'll be assigning the loads here itself, right? So I'll click this node, I'll select this node, I'll go to assign load data, point loads, and here I'll be assigning the gravity load. For the dead load, it is 1000 kilonewton, and make it to replace and click on OK. Again I'll select this point, I'll go to assign load data, point loads, I'll change the load case to live, and I'll assign a load of 1000, and it will be 1300 kilonewton, replace. Okay, so two load cases we have assigned. If you just go to 3D view here, and if I turn off this I can say, let me see if I can turn off the, I think I can turn off this from here, axis. Okay, so you can see if I just go to display, show loads, so dead load of 1000 kilonewton and a live load of 1300 kilonewton I have assigned here. Fine. Now I'll go to the plan view again. Now one more load that we have to assign in this I can say footing, but this load will be changing. Okay, so what we can do, first of all, taking the initial thickness, which is 400 mm, we will calculate that load. So I'll go to the whiteboard here. So we have considered the thickness of the footing as our you can say 400 mm thickness, right? So what will be the overburden load on this particular footing? So initially the process is, it will be gamma into H. So gamma is nothing but the unit weight of soil. So suppose it is 18 kilonewton per meter cube. It will be given in the soil report, multiplied by this height. So this height, this is the H. What is this height? So if it is 1500, and if you can say this, we have considered initially, suppose trial 1 we have taken as 400 mm thick. So 400 mm will be deducted, so it will be 1.1 meter, right? This is the overburden load that we are considering, right? But if you see, if you want to do it in more precisely, in that case what you have to do, you have to deduct this area also. You have to deduct the area of the column also, but for now we are going in a conservative side, so we are not deducting it. But actually, if you see, this is my footing area, this is my column area. So first of all, you have to find this area. Okay, so this is my 9 meter square minus 450 by 450. This area you have to do. So let us see if we can do this, but we will not assign it, we will do in a simpler way. But just to show you, 9 meter square minus 0.45 multiplied by 0.45. This is my column area. So we got an area of 8.7975. So suppose it is 8.8. I'll just take 8.8 is my area, right? On this area, a load will be applied, which is this gamma into H. Okay, which is this gamma into H. So this is how you need to do it. Just you have to find out this load per meter square, right? Load per meter square, then you need to apply it on the footing area. So you'll be getting it in kilonewton. But we are not doing it, we will be doing it in a very simpler way. We will just multiply gamma into H. Okay, so we will get, this is I think, yes, so we'll be getting the load in kilonewton per meter square. So how much it will be? 18 into 1.1. so I'll just do it, 18 multiplied by 1.1 equal to, we are getting 19.8 kilonewton per meter square, right? Because here, if you see, you can always compare. If you are getting confused, you can always compare with this unit. So this meter is at the top, this meter cube is at the bottom, so here we will get meter square, right? So kilonewton per meter square. So this is the area load that we have got for per meter square. So this area load will be applying as the overburden load on our footing. So I'll just click on this, I'll select the footing. Here you can see a green color highlighted area will be showing, that means this area is selected. I'll go to assign load data. Now it will be a surface load, so I'll just click on this surface load. I'll take the you can say load case I have created to define the overburden, and it will be 19.8. so you can say that 19.8 it was, right? Okay, so you can say 20 kilonewton per meter square load will be added. So I'll just replace, click on OK. Okay, so the overburden load is also applied here. So I'll click on this show undeformed shape. Fine. Now, so we have defined the area, we have defined the load on it. Now what we have to do, we have to define the soil, because this particular footing will be resting on the soil, right? So if you see, this is my footing, we have the column and loading here. So now it will be resting on soil. This is my soil, and this soil will extract reaction pressure on the footing, as the load will be coming from the footing also, right? And this reaction we all know will be giving ground bearing pressure or GBP, whatever it is. You can call it bearing pressure also. Now the thing is how we can define this soil property. So the very simpler process of defining the soil property is the springs. If you see here that what we do basically, whenever you see the, I can say, soil report, that at the soil report will be given in this way, that at 1.5 meter depth for some 25 mm or 50 mm or 12 mm settlement for a foundation size of 1.5 by 1.5 meter, this is the QA SBC. For a foundation size of 2 meter by 2 meter, this is the QA. So here two criteria are there. One is the area of footing, another one is the settlement of the footing, and at what depth. Okay, so depth we have considered. Okay, depth will not be useful because here we are not you can say doing any soil modeling, direct soil modeling. So we have just assigned the load for the overburden considering this depth. Now area also we have calculated, and for this area suppose we have got a you can say SBC that we can consider, which is 300 kN per meter square. Now one more thing is there, is the settlement. Okay, so why this settlement criteria is given? So how we can use this settlement criteria? So basically what we do, suppose this is my footing bottom and this is the face which is in contact with the soil property. So what we do, we define some springs here, like this. Okay, we define some springs here like this. So what will happen here in case of spring? Suppose this is my spring here, at the bottom it is fixed. So what will happen here? So once we give some load on it, suppose this is the load on it, initially what will happen? The spring will shrink, right, like this, up to a certain limit. So from here to here it will shrink, right? I'll do like this, right? So after a certain point, once it is like this, so it is unable to shrink anymore, what will happen then? Then it will try to resist this load. Okay, then it will try to resist this load, right? So this, due to this shrink, the footing will go down from this level to suppose this level, and this settlement we have defined as 25 mm for isolated and combined footings. Okay, that how much it should settle down. Okay, how much the soil should settle down. Okay, so this phenomena can be defined using some springs. Now what should be the stiffness of the spring? Okay, because the amount of stiffness will be assigning to the spring, that amount of force it can resist, or that amount of force it can attract, right? So settlement we have defined, right? So we need to define the stiffness. The stiffness will be in terms of subgrade modulus. subgrade modulus. Okay, so how we can define this subgrade modulus? We know the soil bearing capacity, how much the soil can bear for that particular certain size of footing, and we know the settlement. So we will be up to a certain limit, we'll be allowing a settlement, and then we will ask or will be giving command to the spring that it should resist the load after the settlement. Okay, so the capacity we know it is 300 kilonewton per meter square, and we know the settlement. So the spring constant, or for area load, or you can say for area footing, or you can say isolated or combined footing or raft, we call it as subgrade modulus. For piles it will be spring constant. So the subgrade modulus K, we will define it as my SBC 300 kilonewton per meter square divided by how much settlement we are allowing. So the settlement we are allowing 25 mm, so I'll just convert it to meter, 0.025 meter. So the, you can say, unit of spring constant will be getting it as kilonewton per meter square per meter. Okay, this is the unit we will be getting, right? So this is how we can model the soil here, or we can assign the soil property to the footing, right? So here the soil property will be defining using the subgrade modulus, and then we need to analyze the footing for you can say checking of ground bearing pressure, and to check whether the sizing that we have provided initially, it is okay or not. If the pressure that the soil is extracting on the footing is more than our bearing capacity, in that case we will understand that the load coming from above is more than this 300 kilonewton per meter square on the soil, right? Because this is the reaction. So what the amount of action that will give, the same amount of reaction in the opposite direction will be getting, right? The basic concept we all know. So that's why by seeing the pressure diagram we can understand how much amount of load is coming on the soil from the footing, right? If it is more than this, the soil is not capable of taking, so we need to increase the area of the footing. Okay, so sometimes we do not see what is the, I can say, SBC defined after that area. So suppose for 2 meter by 2 meter area, the you can say SBC is defined as suppose 210 kilonewton per meter square. And now we have seen that this area is not sufficient, but we have taken 3 meter by 3 meter area, but we kept the SBC limit as 210 kilonewton per meter square. Okay, so this will not work, because with the increase of size of footing, the SBC reduces actually. So you have to always look back to your you can say soil report, and you need to see that the sizing that you are getting now, what will be the SBC it can take for that particular size. Fine, maybe the exact size will not be matching, but the you can say nearby value you need to cross check. But for now we will consider that the SBC is constant, which is 300 kilonewton per meter square. Okay, for this particular you can say isolated footing. So I'll keep this session up to here only. In our next session, what we will do, we will define the subgrade modulus, we will assign this soil property to this footing, and we will try to see how we can analyze the footing, and we can size, we will check the initial sizing of the footing. Okay, so we'll see you in the next lesson. Thank you, and if you have any doubt, you can always ask me in the comment box. Thank you, and see you in the next lesson.